Right. Hello, welcome to your Math 181 Exam 2 review. My name is Carl. I'll be running your review session today. So there's currently no one in this break room with me, so I'll just be talking to those of you watching on YouTube. All right, so I was given this practice material with 10 questions, I believe. So we're just going to go ahead and just start from the top and work our way through. All right, so question 1. Compute this derivative right here. All right, let me just go ahead and set everything to how I like it. All right, computing this derivative. So we got ourselves, the function is a fraction. So if you guys remember, we have our derivative quotient rule, where if we have, let's say, if we're taking the derivative of some function f over some function g, the derivative ends up being the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Right. So in this case, our top function, our f, is e to the x, and our bottom function g is 2 minus x to the fourth. So following the quotient rule, we're going to go ahead and just fill in the blank, right? So then the derivative is equal to the derivative of the top. So the derivative of e to the x is just e to the x times the bottoms, which is 2 minus x to the fourth, minus the derivative of the bottom. So the derivative of the bottom is, well, let's take a look. 2 minus x to the fourth. So the derivative of 2 is 0. The derivative of minus x to the fourth, it's power rule. So you bring down the 4 and you decrease the exponent. So this would be minus 4x cubed. That's the derivative of the bottom. Times the f of x, which is the top. So let's just e to the x again, all over the bottom squared. 2 minus x to the fourth squared. All right, and then we're just going to simplify this a bit further. So if we look at the top, we have e to the x times 2 minus x to the fourth, and then the negatives cancel out. So this will be plus 4x cubed e to the x. And now we can all over 2 minus x to the fourth squared. And this is technically a valid answer. You could say you're done here. I'm just going to do one more step to make it look a little nicer. I'm going to factor out this e to the x on the top. So all I'm left with is 2 minus x to the fourth plus 4x cubed all over 2 minus x to the fourth squared. And that right there is a valid answer as well. All right. So it depends on how your professor prefers it, how simplified he wants your answers, but both are valid. All right, let's go to part B. Find the first derivative and second derivative of f if f of x is x to the 9th times ln of x. So this is going to be a bunch of product rules, it looks like. So let's first take f prime. So well, first of all, let's just make sure what we know what the product rule is. If we're taking the derivative of the product of two functions, so let's say f times g, then it's going to be the derivative of the first times the second plus the derivative of the second times the first, right? So if we let this be f, let's let this be g, we go ahead and find the first derivative using product rule. So derivative of the first, derivative of x to the 9th, bring down the power, decrease the power by 1, that's 9x to the 8th, times g, which is ln of x, plus the derivative of the second, so derivative of ln of x is 1 over x, times the derivative of times the first function, so that's x to the 9th. If we simplify this out, we'll get 9x to the 8th ln of x plus x to the 8th. So if we really wanted to, we could leave it like that, or we could even simplify it further by factoring out the x to the 8th. We'll get x to the 8th times the quantity 9 ln x plus 1. And that right there is also valid. All right. And yeah, so taking a look ahead, Depending on where you stop, your process might be slightly different, but you should get the same answer. If we were to take the second derivative of f now, we have to readdress what is our first function, what is our second function. And that's why I say it depends. The process is slightly different depending on how far you simplify. If you stopped here, then if we take a look, we have two terms added to each other. So we can sort of take the derivative of each term separately. This is very easy to do because it's just one power rule. But this right here is another product rule. So if you're going to do, if you're taking the derivative, the second derivative starting from this form, make sure you reset what is f, which will be this, and what is g, which will be this, right? So that's if you're going to do it that way. If you simplify to this, then this is just one term. It's product rule. This will be f and this will be g. So it's really your preference, because I feel that most people will stop probably here. Let's go ahead and take the derivative of 9x to the 8th times ln of x plus x to the 8th. So first we got to handle this first term right here, which is going to be a product rule. So it's the derivative of f. So what is the derivative of 9x to the 8th? Well, bring down the power. We'll have 9 times 8 x to the 7th times the g, which is ln of x, plus derivative of g, which is 1 over x, times f, which is 9x to the 8th, plus, now we have to do the derivative of 8 of x to the 8th, which is just bring down the power, subtract the power. So 8x to the 7th. And this right here is our second derivative. If we go ahead and simplify this further, 9 times 8 is 72, x to the 7th ln of x, plus 9x to the 7th, plus 8x to the 7th. And we can actually simplify these last two terms here. This would be 72 x to the 7th ln of x plus 17x to the 7th. And like we did up here, you could either stop here or you could pull out the x to the 7th and you'll get x to the 7th times 72 ln x plus 17. Both are valid answers, right? So again, it depends on how far your professor expects you to simplify. Yeah, that's B. Let's go ahead and just move right along to C. Find the first derivative given this function. Okay, so this is again a product rule thing. We got sine of x as our first function and secant x squared as our second function. So before we continue on, though, we'll probably want to remember what some of our trig derivatives are. So go ahead and if you have notes on it, great. If you don't, just easily Google trig derivative rules, and you should you'll be able to follow along with what the derivatives of these trig functions are, right? So let's go ahead and plug it in now. So the first derivative is take f prime, which is the derivative of sine is cosine x times g, which is secant of x squared, plus derivative of g. So the derivative of secant is secant tangent. So let me go ahead and write that down. The derivative of secant x is equal to secant tangent, right? But let's not forget, though, that we have a function within a function. So this is actually chain rule. So if we have secant of a function inside, let's say f, for example, we have to follow chain rule, right? We have to first take the derivative of the outside, which would be secant f of x tangent f of x times the derivative of the inside, so the derivative of f of x. So that's sort of the general form. What does that actually mean in our case? Well, first let's do the outside. So remember, the outside function secant, the inside function is the x squared. So in order to take this derivative following chain rule, derivative of the outside is the derivative of secant, which is secant, copy the inside, secant x squared times tangent x squared. So secant tangent, this is the derivative of the outside function. Now we have to multiply this whole thing by the derivative of the inside. So the derivative of x squared is 2x, right? And now we just go ahead and see, can we simplify this a bit? Well, yes, we can actually. So let's remember that, actually, no, we can't. I take that back. Yeah, this is probably as nice as it'll be, so you can go ahead and leave your answers as this, right? So cosine x times secant x squared plus secant x squared tangent x squared times 2x. If you want to bring this to the front of that, that's totally fine, but this is a totally valid answer. Yeah, so things to remember. What are your trig derivatives? And more importantly, don't ever forget chain rule. If you have a function within a function, then you have to apply chain rule, derivative of the outside times the derivative of the inside, right? So just that's something to remember. Let's go ahead and move on to question part D. We have the 33rd derivative of y given y is equal to cosine x. So something you should maybe recognize is, let's sort of treat this as the 0th derivative. Let's go ahead and try to find the first derivative. The first derivative, what's the derivative of cosine? That's minus sine x. If we take the second derivative now, so the derivative of negative sine x is negative cosine x. And the third derivative is of the derivative of negative cosine x is simply sine of x. And if we take the fourth derivative of sine x, so if we take the fourth derivative, this will become cosine x, right? So if we take a look here, we can sort of think our original function, or the quote unquote 0th derivative, is equal to the fourth derivative of cosine x. And if we take a look, just if we try to find the fifth derivative, this will be negative sine x, right? Which is equal to the first derivative. So as we can sort of see, it's sort of a cycle, right? We go from the original function to the first derivative, to the second derivative, to the third derivative, and technically we go all the way back. So it's sort of in a loop, right? A cycle. So we're going to use this property of the derivative of this trig function to figure out what the 33rd derivative is. So if you, the trivial way would be to continue going y to the 6th, y to the 7th, so on and so forth until you get to y to the 33rd derivative, but that's going to take way too long. So we're going to use this cyclic property, right? So in order to figure out what does y to the 33rd equal, we're simply going to just divide this. If we sort of divide, notice how the cycle has 4 terms. What we can do is we could sort of think of it as we could try to divide the number and try to find which one does it equal to. So for example, we know for sure that y to the 5th derivative is negative sine x, which is the same as y to the first derivative. So let's take a look at some interesting properties here. If we took 5 and divided it by 4, what do we get? We get 1 remainder 1, right? So, and if we take a look here, the key part to know here is what is the remainder? The remainder in this case is 1, and notice what the derivative actually corresponds to, equals to the first derivative, right? So if we were to go ahead and just try something out, if we were to find the 6th derivative real quick, you can take it from the 5th derivative, which would be the derivative of negative sine x, which is going to be negative cosine x, right? So, but if we divided 6 by 4, we get 1 remainder 2, right? Let me fix that, sorry. We get 1 remainder 2. So if we take a look at the remainder now, that's 2. And that actually corresponds to the second derivative, which is what y to the 6 equals. Y to the 6th derivative is equal to the second derivative. So hopefully you can start seeing the pattern here. Whatever nth derivative of a trig function you have, if you simply divide by 4 and take the remainder, so 33 divided by 4 is 8 remainder 1. If you take the remainder, that corresponds to that nth derivative. So if we have remainder 1, that corresponds to the first derivative. So the 33rd derivative of y is simply equal to the first derivative of y, which is equal to negative sine of x, right? So that's the sort of trick you want to use here. If you have a single trig function like sine or cosine, list out the first 3 derivatives, or 4 technically. Just remember that the original function is always equal to the 4th derivative if it's a single trig function. And then you can go ahead and apply this sort of cyclical rule. Divide the nth derivative, so the n divided by 4, find the remainder and take that derivative. So yeah, that sort of corresponds with everything, right? And just to clarify, if you ever run into remainder 0, that simply means it's the original function, right? That's why I sort of treated this as sort of the 0th derivative in a sort of sense, right? So yeah, that's the sort of trick you want to use in this case. Of course, you could write down y to the 7th, y to the 8th, y to the 9th, all the way up to y to the 33rd, but that's going to take a little long. So if you can recognize the pattern, you can sort of easily skip ahead to the ending, right? All right, so that's the sort of trick used in this part. Let's go ahead and go to part E now. Find the first and second derivative if y is equal to this. So this is very straightforward. We have, this is technically chain rule. So we have this outer function, which is an exponential function, e to some power, but the power itself is a function. So we have sort of this deal going on, right? So if you take the derivative of this whole thing, following chain rule, so the derivative of the outside function would be the exponential, and the inside function would be the power itself. So what's the derivative of an exponential? Well, it's the copy of itself times the, it's the copy of itself, right? So now but now we have to find the derivative of the inside. So we have to actually multiply by the derivative of the power. So we multiplied by f prime of x, right? And if we go ahead and do that now, what do we get? Y prime is equal to, well, derivative of e sine to the x is e sine to the x times the derivative of sine x, which is cosine x, right? And now if we try to take the second derivative, we have to apply the product rule now. We have sort of this as our f and this is our g. So if we first do the product rule, remember it's going to be f prime g plus g prime f. So the derivative of the first, well, what is the derivative of e sine to the x? Well, we actually know this already. If you were to go ahead and calculate it again, but if you recognize that was the original function we started with, and the derivative of that was y prime. So it'll just be e sine of x times cosine x. That is the derivative of f prime. Now let's go ahead and multiply it by g, which is cosine x, plus g prime. So the derivative of cosine x is minus sine x. And then f is e sine to the x. And if we go ahead and simplify this a bit, we have, what do we get? E sine x times cosine squared of x minus sine x e to the sine x, right? And that's right there. You can leave your answer like that. Perfectly fine. All right, let's go ahead and move on. Part F, find the derivative, right? Okay, so we have this sort of same deal going on here. We have chain rule again. We have our outside function, which is an exponential with base 2, and then we have a function within the exponent, which is our inner function, right? So let's let this be f, let's let this be g. So something that we need to know, what is the derivative when the base isn't e? Well, in case you don't remember, if let's say you're taking the derivative of this, so the derivative of some base a, right, to the power of x, the derivative of that is going to be a copy of it. So you write the same thing, multiply it by the natural log of the base, so the natural log of a, and then let's go ahead and generalize it. So if we have a function inside the exponent, really it's going to be a to the x times ln of a times the derivative of the exponent, right? So it'll be the derivative of f. And that's going to be the sort of property we're going to use here. So that's what this whole thing is. This is the general chain. This is chain rule applied already. So with chain rule applied already, we can sort of answer this question. So f prime is going to be equal to, well, a to the exponents, sorry, so f of x, a to the exponent. So it's just going to be a copy of it. So it'll be 2 times 3x to the x times ln of the base. The base is 2, so ln of 2 times the derivative of the exponent. So if the exponent is 3 to the x, right? So we need to find the derivative of this first. Well, the derivative of this follows this exact same rule, right? So it'll be 3x times ln of x, ln of a, rather. And the derivative of x is just 1, so we just leave it alone. So the derivative of this exponent, 3dx, is this right here. Yeah, so we're going to be multiplying it by 3x times ln, sorry, what did I write? Ln of a, this is ln of the base, which is 3. So this is times ln 3. So this right here is the derivative of this. We can sort of simplify it just a little bit. We can write it as 2 to the power of 3 to the power of x times 3 to the power of x times, can you multiply that together? No, I think we just keep it as ln of 2 times ln of 3. Yeah, never mind. You could just keep it as that. I don't think you can simplify this further. At least I'm not remembering a way off the top of my head. But yeah, let's go ahead and move right along then. Let's go to G, y prime if y is equal to cosine squared of tangent of x. So this is chain rule again. Here's our out, here's our in. So let's go ahead and follow along. Derivative of the outside. So what's the derivative of cosine squared? So it's power rule. So we bring down the 2, write down cosine, and write down the inside the exact way it is. Now we have to find the derivative of... Oh, wait a minute. We also have to multiply this by the derivative of cosine, I believe. Am I remembering this correctly? If you have cosine squared of x, and you take the derivative of that, what is that? It's the same as taking the derivative of cosine of x, that whole thing squared. Yeah, so this would be then 2 cosine of x times sine of x, I believe. Let me double check that. I'm brain farting right now. Oh, shoots. I got this completely wrong. Or did I? No, I didn't. Let me double check something. Just want to double check that I'm giving you the right information, because I think this uses a very interesting property. Where's the... so yes, okay. So I am right. Okay, so this has like a chain rule within a chain rule. So it's like a nested chain rule here. So let's go ahead and look what's going on here. So if we sort of look at the simple case first, we have the derivative of cosine squared of x is going to be, we sort of have, the reason why I say this is a chain rule in the chain rule, the derivative of cosine squared is actually a chain rule of itself. We have the inside function, which is the cosine, and the outside function is the power. So if we do take the derivative of this, we do the power rule first. So bring down the 2 cosine, take down the power. So this would be cosine of x. But now we also have to multiply it by the derivative of the inside function, or the inside function in this case, as we can see clearly in this one, is cosine. The derivative of cosine is minus sine, right? Minus sine of x. So the derivative of cosine squared is -2 cosine x sine x, right? Why do I bring this up? Is because we have that same situation here. Within this part right here, the cosine of cosine squared, the cosine is the inside function, and the power 2 is the outside function, right? So we can sort of rewrite this to see it clearly as cosine of tangent x, all of this squared. So we have, this is our outside function. The cosine is our inside function. That's for the first chain rule. And then if we think of the second chain rule, we'd even see that this is the inside function and this is the outside function, right? So we got double chain rule going on here. So let's first deal with the outer chain rule first. So the outer chain rule is the derivative of cosine squared, right? So the derivative of cosine squared is 2 cosine times whatever's inside of it, times the derivative of cosine, which is minus sine of whatever is inside of it, so sine of tangent x, right? So that covers the the first part. That covers the derivative of this outside function, or this entire cosine squared, right? So now we have to take the derivative of tangent. So the derivative of tangent, and we multiply that in, the derivative of tangent is just secant squared of x, right? So lots of just take a moment to really understand this concept. Again, to sort of clarify it out, let me go to rewrite everything down here. We have this going on, cosine squared of tangent of x, right? Which we can sort of visualize as this. Cosine of tangent x, all of this squared, right? So when you're taking the derivative, we got to take this is chain rule. So the derivative of the outside function, in this case, this whole outside function is cosine of let me put this to the side for now. Something popped up. Oh boy. Okay, hopefully that doesn't break anything. Okay, sorry about that. So the outside function in this case is cosine. The derivative is cosine squared, and the inside. Yes, this is the outside. And the inside is the tangent. So first, following chain rule, is we have to take the derivative of the outside. So what is the derivative of cosine squared? Well, it's this right here, right? The -2 cos x sine x. But instead of x, we put tangent x. So that's what we got right here. And then we have to multiply it by the derivative of the insides. And the derivative of the inside is the derivative of tangent, which is secant x, which is right here, right? So that's how we got that whole deal. So sort of take a moment, understand how that works, because this is pretty complex. This problem right here actually has nested chain rule, which is a little tricky. All right, so let's go ahead and simplify this out. So we'll get -2 cosine of tangent x times sine of tangent x times secant squared of x. Well, you can actually simplify this further. Let's remember what secant is. Secant is of x is equal to 1 over cosine of x, right? So all secant squared of x is 1 over cosine squared of x. So really we have -2 cos tan x sine tan x times 1 over cosine squared of x. And we can see we can actually no, we can't cancel it. So I thought we could, but we can't. And the reason why, look at this. Inside the cosine function is tangent x. I can't highlight it, that's odd. Inside the cosine function is tangent x. Inside the secant function is x. Because the insides are not the same, we cannot simplify it. So actually, I would go ahead and stop at this step right here. This would be our final answer. I thought I could simplify, but we can't because the insides are different, right? So realizations, we got to always watch out for that. All right, let's go ahead and move on. Letter H, y prime if y is equal to this whole stuff. Okay, well, now we're getting into the inverse trig functions. So go ahead and pull up on Google, just Google trig derivatives, inverse trig derivatives. If you don't remember this off the top of your head, I certainly don't. So something that I want to note is that the derivative of sine inverse, again, sine inverse and arcsine are the exact same thing, right? So the derivative of sine inverse is equal to 1 over the square root of 1 minus x squared, okay? And of course, since in this case we don't have x, we have 3x, so we're gonna also have to apply chain rule there, right? So let's first label x as f, f is g. This is product rule first and foremost. So product rule says derivative of the first, derivative of x is 1, so it's just going to be arcsine of 3x plus derivative of the second. So what's the derivative of arcsine? the derivative of arcsine 3x is going to be this 1 over square root of 1 minus parentheses 3x squared. Remember, this x has to represent this whole inside. But we also have to apply chain rule because there's a function within a function, right? So we're multiplying by the derivative of 3x, which is times 3. Now that was just the derivative of g. So now we have to multiply it by f, which is just x, right? So if we go ahead and simplify this out, we have arcsine of 3x plus 3x all over 1 minus 9x squared, right? And that right there is our derivative, right? So this is starting to introduce the trig functions, right? And then if we take a look at I, we've got chain rule again, except this time it's with an inverse trig function. And just in case you don't remember, the derivative of tangent inverse is equal to 1 over 1 plus x squared, right? But in this case, we're not using x, we don't have x, we have cosine x. So we have to do chain rule again. So this is your out, this is your in, right? So let's go ahead and try to find the derivative. So the derivative of the outside is going to be this tangent function, this tangent inverse function. So it'll be 1 over 1 plus, not x, but cosine x squared, right? Now we have to multiply it by the derivative of the inside. So the derivative of cosine is negative sine of x. And now what do we got here? Can we simplify this? Well, actually we can. Oh, maybe you can't. Oh, that's unfortunate. This would have been really nice if you could simplify it that way, but you can't. Yeah, so we can just simplify it as negative sine x all over 1 plus cosine squared x. Yeah, I thought that we could simplify something going on here, but no, we can't. Yeah, 1 plus cosine squared x wouldn't help us, I don't think. Or does it? No, it wouldn't. Yeah. So we can just sort of leave it like this, and that would be your answer. Negative sine x over 1 plus cosine squared x. Okay. I'm pretty sure that doesn't simplify, so we're going to leave it alone. All right, so that is I. We're going on to J now. Okay, so we got some derivative log rules, except the base is not E. So in case you don't remember, what is the derivative of log base B of x? Well, I believe it will be 1 over ln of b times x, I think. Let me go ahead and double check that. Yes, natural log of b times x. And of course, if this is a function, then you have to do chain rule, right? Multiply it by the derivative of the inside. So let's go ahead and take this. What is this derivative? Well, we do have a chain rule. This is our outside, this is our inside. So the outside is the derivative of log base 6. Well, what is that? That'll be 1 over ln of the base, which is 6, times whatever's inside. So that'll be times x cubed plus 1. But we also have to now do chain rule, multiply it by the derivative of the inside. The derivative of x cubed plus 1 is 3x squared, right? And now if we go ahead and simplify this, we got 3x squared over ln of 6 times x cubed plus 1. And that's all it is. Very straightforward. It's just remembering your general derivative log rule, right? All right, looking at K now, we've got chain rule again with the trig function. So let's just go ahead and straight through this. The derivative of cosine is minus sine of the inside. Now I have to multiply it by the derivative of this inside thing. So there's two terms. So the derivative of x to the fourth is 4x cubed, plus the derivative of 4x. Well, if you remember, this is going to be our general exponent derivative rule, which will be copy the exponent, copy the exponential, multiply by ln of the base, right? So this right here is your final answer. All right, it's just double checking your understanding of chain rule and all that stuff. Looking at L, Again, this is going to be a chain rule sort of thing because we have an exponential to some function. So what is f prime going to be? Well, the outside function is the exponential. The inside function is the exponent. So what's the derivative of an exponential? Well, you copy the exponential, multiply it by ln of the base. That is the exponential. Now we got to do the derivative of the inside or the exponent. The derivative of arctangent is 1 over 1 plus x squared, right? So if we go ahead and put this all together, we get 2 ln 2 all over 1 plus x squared. And that right there is your answer. Right, so I'm sort of speeding along here because we're still on question 1. There we go. Now we're on question 2. Now we're doing limits. Okay, so whenever you have a limit, first thing you want to do is just plug in the value and see if it gives you an answer, right? So if we plug in 0 into this, what do we get? We get sine of 0 over tangent of 0. And what is sine of 0? Well, sine of 0 is 0. And tangent of 0 is also 0. So right here, what we have 0 divided by 0. Uh-oh, that seems like an error, but really it's an indeterminate form. I believe that's how you spell it. And because we have an indeterminate form, we can go ahead and apply L'Hopital's rule, right? If we apply L'Hopital's, that means that this limit is actually equal to the limit of the numerator's derivative over the denominator's derivative, right? So let's take that. What's the derivative of sine of 3x? That is 3 cosine 3x, right? So that's, again, chain rule. I just get the step. The derivative of sine is cosine. The derivative of 3x is 3. So 3 cosine of 3x times 3 is 3 cosine 3x, right? And then doing chain rule for the bottom as well, it'll be 7. The derivative of tangent is secant squared. So secant squared x, right? Oh, secant squared of 7x, sorry. All right, so what happens when we plug in 0 now? Well, let's see. We have 3 over 7 times cosine of 0 over secant squared of 0, right? So what is cosine of 0? Well, cosine of 0 is 1. And what is secant squared of 0? Well, let's remember that secant squared of x is equal to 1 over cosine squared of x. So secant squared of 0 is equal to 1 over cosine squared of 0. Well, we know that cosine is 0. Cosine of 0 is 1. So cosine squared of 0 is 1. So secant squared of 0 is 1 over 1 or 1 as well. So this simplifies out to 1 as well. So, and what are we left with? We're left with 3/7. So by L'Hopital's rule, because the original limit was a fraction where the limit of the top is 0 and the limit of the bottom is 0, creating an indeterminate form, we're able to apply L'Hopital's rule, which says you can take the derivative of the top and the derivative of the bottom and take the limit of that new function. And that'll equal the same limit. So that's how we got 3/7, all right? L'Hopital's. Let's go ahead and do this one. Question B is also using, well, as we'll see, it'll also use L'Hopital's. What happens if we plug in 0? We'll get sine cubed of 0 over 0 cubed. Well, we already know sine of 0 is just 0, so we'll have 0 over 0. This is, again, the indeterminate form. So we're going to use L'Hopital's. So what's the derivative of sine cubed? Well, let's figure that out. Oh, that is horribly written. The derivative of sine cubed is, well, the derivative, it's like again, another chain rule sort of thing. So we have the derivative of sine cubed is the outside. So what's the derivative of sine cubed? Well, it'll be 3 sine squared of whatever's inside times the derivative of sine, which is cosine of the inside. And now that's this whole thing dealt with. Now we also have to take the derivative of 2x, so times 2, right? And then we divide that all by the derivative of x cubed, which is just 3x squared, right? So what's some things we can cancel out here? The 3's cancel out, and that's it. So let's go ahead and rearrange this real quick. So we got the limit as x approaches 0 of 2 sine squared of 2x times cosine of 2x all over x squared, right? Well, what's going to happen here? Let's see. If we plug in 0, what does that give us? We'll have 2 sine squared of 0 cosine of 0 all over 0 squared. And this, because sine squared of 0 is equal to 0, we'll get 0 over 0 again. So we're going to have to do L'Hopital's one more time. So we'll do L'Hopital's once more using this step right here. So, or this, more specifically, this function right here. What is that? Let's see. Now we've got even more chain rule. We've got product rule as well. So we've got these two functions. So the derivative of the first function, that's 2 sine squared of 2x. So the derivative of that would be, let's do the power rule first. So the derivative of sine squared, that'll be 2 times 2. So this 2, the first 2 is the constant. This 2 is the power. So I brought down the power of 2 times sine of this whatever's inside times the derivative of sine, which is cosine of whatever's inside. Now I have to multiply this whole thing by the derivative of the inside, which is 2x, which is times 2, right? And that completes the derivative of the first function. Now we multiply this whole thing by the second function, so times cosine of 2x plus the derivative of the second. So the derivative of cosine is minus sine of x times the whole original. So that'll be, the derivative of cosine of 2x is not minus sine 2x. It's not minus sine x, sorry. It's chain rule, so the derivative of cosine is minus sine 2x times the derivative of the inside, which is 2. So it'll be minus 2 sine of 2x times 2 sine squared of 2x, right? And this is all over x, or 2x rather. So let's go ahead and simplify this out. What does this simplify out to? So we have the limit x approaches 0 of, this is 2 times 2 times 2, which is 8. 8 sine of 2x times cosine squared 2x plus, no, minus, because the negative right here, minus 4 sine cubed of 2x. Yeah, all over 2x. And if we still plug this in, or we can simplify this out, so I can divide 2 from all this. This will be 4, and this will be 2. Well, what are we left with? We have 4 sine, if we plug in 0, with 4 sine of 0 times cosine squared of 0 minus 2 sine cubed of 0 all over 0. So you're going to have to do L'Hopital's once more, which will give you this whole thing, right? If we do L'Hopital's once more on this function right here, we have to take the derivative of this whole thing again, right? It's a little painful, but it is what it is. So let me just go ahead and rewrite this real quick. What is this function? That's 4 sine of 2x cosine squared of 2x minus 2 sine cubed of 2x all over x, right? So that right there is the function from this. So if we take the limit once more using L'Hopital's, what do we have? So I'm just going to sort of jump ahead real quick. So just one thing to note, the derivative of x is 1. So the denominator is now gone. And what are we left with is the question. So we just need to find the derivative of this numerator. So we have a power rule going on here, 4 sine of 2x times cosine squared of 2x. So the derivative of 4 sine of 2x, that is 8 cosine of 2x. So that's the derivative of the first times the second plus the derivative of the second. So the derivative of cosine squared is going to be 2 cosine of 2x times negative sine of 2x times the inside, that's 2. Yeah, and now this is times the first function, so times 4 sine of 2x. And then we have to subtract 2 sine cubed of 2x, 2 sine cubed of the derivative of 2 sine cubed of 2x. So that'll be power rule again. So it'll be 2 times 3 of sine squared of 2x times cosine of 2x times 2. Right? And if we simplify that further, well, actually, we can actually figure out the answer right now. If there anywhere with a sign, if you plug in 0, it's 0. So right here, this middle term and this last term both have signs in it. So these terms go to 0 when you plug in x. So all we're looking at is right here, and cosine of 2x, cosine of 0 is 1. So this is also 1. So the answer is 8, right? So that was a lot of work, a lot of L'Hopital, but it ends up simply being 8. And yeah, now that I think about it, there actually might have been a way easier way to do this. I think the easier way to do it is using a property we know. If you have the limit of x approaches 0 of sine of, let's say, a square. So this square could be anything, and it's over the square. This is equal to 1, right? So I think you can actually rearrange this. So yeah, that would have been a lot faster than what I did. But if you had the limits of x approaches 0, so what I'm going to do a little trick. I'm going to multiply the top and bottom by 2 cubed. So I can do that because 2 cubed over 2 cubed is just 1. So all I'm doing is I'm multiplying this factor by 1, but with specific numerators and denominators, right? Reason why I did this is now I can rearrange this as the limit as x approaches 0, 2 cubed on the top, that's just 8. Sine cubed of 2x over 2 cubed times x cubed. I can sort of write that as 2x, all of that cubed, right? And now what I can rewrite this even further as the limit as x approaches 0 of 8 times sine of 2x over 2x, all of that cubed. And this is where we can start seeing some things, right? This right here matches this property, this identity right here. So that means that this whole thing inside is just equal to 8 times 1 cubed. So this whole thing's equal to 8. That would have been the way faster method, but that's if you remembered, like I didn't, remembered this identity right here. But yeah, that's a lot faster compared to taking L'Hopital's 3 times. But yeah, this goes to show that if you forget it, you can take the L'Hopital's 3 times and still get the same answer. But this is way faster. Just remember this identity. You'll save yourself some time, right? So yeah, and then just again, manipulating it in such a way, multiplying it by 1, but in such a fashion that you can sort of create this identity right here. Yeah, so I'm a little upset at myself that I didn't see that right away, but yeah, it happens. If you don't see it, you could proceed with L'Hopital's 3 times, but in this case, way faster to do this, right? All right, let's go ahead and move along. We might need to start skipping questions because we've got about half an hour left. Implicit function. Okay, so this is very straightforward. Let's start just taking the derivatives of things. So I know some people, we're going to be calculating y prime. Again, some people like writing y prime as dy dx. Totally fine. If you like writing it like that, by all means do that. I'm going to keep it as y prime. So all we need to do is take the derivative of both sides with respect to x, right? All right, so derivative of y cubed, that'll be power rule, so 3y squared times the derivative of the inside, the derivative of y, so it'll just be y prime. Just like that, right? Very straightforward. Derivative of 3xy is product rule, so the derivative of the first, so the derivative of 3x is 3 times y, plus the derivative of y, so that's y prime times 3x, plus the derivative of 3x squared, of x cubed, that is 3x squared. And then the derivative of 12 is 0. Right, so now what we want to do is we want to factor everything such that we have only y primes on the left, everything else on the right. So what do we have? 3y squared y prime plus 3xy prime is equal to, so we're going to subtract this term and this term to the other side. So that'd be negative 3x squared minus 3y. And then we can now pull out the y prime on the left. So we'll get y prime times 3y squared plus 3x is equal to minus 3x squared minus 3y. And now we can divide this whole thing so that we have y prime on the left and minus 3x squared minus 3y. That whole quantity divided by 3x plus 3y squared. And that is your answer. You can actually simplify this further. Since every single term on the numerator and the denominator is a multiple of 3, we can actually cancel out the 3's. And this will give us our final answer, minus x squared minus y all over x plus y squared. Right? And you could also, even if you want to bring out the negative from the top, you'll get negative x squared plus y all over x plus y squared. That might look nicer to you, but yeah, that's your answer. Very straightforward process. Looking at sine, I might go ahead and, okay, I'll do one of these just so you have it, but I'm going to try to start skipping ahead because I think this is only problem 3. Yeah, so I'll skip B. Let's go to one of the more harder ones. Let's do D then. All right, so what do we have here? EY sine x, 3 plus tangent xy, right? So again, derivative of the left, derivative of the right. So what do we got here? So we got product rule. So derivative of the first, derivative of e to the y. So that's going to be e to the y times the derivative of the exponent. So that's y prime times sine x plus derivative of the second. So the derivative of sine x is cosine x. And then just copy down the e to the y. That's all equal to derivative of 3 is 0. So we're going to ignore that. And then derivative of tangent xy. So this is chain rule again. The derivative of the outside is tangent. So the derivative of tangent is secant squared of xy. And now we have to find the derivative of the inside and multiply that whole thing. So the derivative of x times y is product rule. So the derivative of the first is 1. So 1 times y is y plus derivative of the second. So the derivative of y is y prime times x. And that whole thing, make sure you put that whole thing in parentheses, right? That whole thing is the derivative of the inside, which needs to be multiplied to the derivative of the outside, right? And now what we need to do is we need to find the terms with y prime in it and put them all on one side. So let's go ahead and just rearrange some stuff. So I'm going to rewrite it like this. So y prime's on the outside. Y prime times e to the y sine of x plus e to the y cosine x is equal to, I'm going to factor this, distribute this in. So what do we have? We have y secant squared of xy plus y prime x secant squared xy. Right? The reason why I did that is now I have individual terms and I can figure out which ones have y prime, which is right here, and put them on one side and put the rest to the other. Right? So let's go ahead and do that. So we have y prime e to the y sine of x. We're going to bring this over. So this will be minus y prime x secant squared of xy. Now we're going to put the rest here. So this is y secant squared of xy. We're going to bring this term to the right. So that's minus e to the y cosine x. Right? And now we can go ahead, we can factor out the y prime from here, leaving us ey sine x minus x secant squared of xy is equal to this whole thing. And then we can solve for y prime by just putting that over it. So our final answer, y secant squared times xy minus e to the y times cosine x all over e to the y times sine x minus x secant squared of xy. And that right there is your final answer. And if you really wanted to, taking a look at everything, is it worth it? No, it's not worth it. Leave it like that. That's your final answer. Yeah, what I was contemplating is if you can get rid of the secant squareds, but no, it's not worth it. Yeah, that's your final answer. And the rest all follow the similar process. So I'm going to go ahead and move on to question 4. So before I move on, yeah, so all of them follow the similar process. It's just making sure you, again, you understand your derivative rules. And once you take, as long as you properly take the derivative of both sides, you want to arrange them so everything with y prime is on one side, everything without y prime is on the other side, so that you can factor out the y prime, and then you can divide the rest so that you get a nice answer like this, okay? That's sort of a very repetitive process. Let's look at number 4 now. So we're doing logarithmic differentiation. So this strategy here is by taking the ln of the function, and then from there, you can go ahead and take the derivative of this to find what the derivative of fx is, right? So taking the natural log of fx, that's the natural log of this whole thing, the square root of x minus 2 over x to the 4th plus x. Let's go ahead and rewrite this so that instead of a square root, we write it as a power. So we have the ln of x minus 2 over x to the 4th plus x, all of that's to the power of 1/2. Now, if you remember our log rules, if the inside of the log is to a power, you can bring the power to the front. So we have 1/2 natural log of x over x minus 2 all over x to the 4th plus x. And even further, if you remember your log rules, you can actually break up this fraction. This is the difference rule of logs. So this will be ln of x minus 2 minus ln of x to the 4th plus x. And this is totally valid to do as well. And the reason why I do that is because this might be a lot easier to work with when we start taking the derivatives. I could be wrong, but let's see what happens, right? So now that we found what ln of f of x is, let's go ahead and find the derivative of ln of f of x. So the derivative of ln of f of x is going to be equal to, this actually might have been completely pointless. Yeah, that might have been completely pointless because we'll see if that was completely pointless. If I take the derivative of ln of f of x, if we remember our natural log rules, that'll be 1 over f of x times f prime of x. Yeah. Yeah, okay. Maybe I'm not remembering this correctly. No, I am remembering this correctly. Yeah, so the derivative of ln of f of x is equal to, this is the general form, but let's also remember that it'll be the derivative of whatever this is right here, right? So we want to take the derivative of this whole thing. Yeah, so taking the derivative of this whole thing, well, if it helps, you can actually rewrite this as 1/2. So you could technically distribute the 1/2. It might be easy to look at. 1/2 of ln of x minus 2 minus 1/2 ln of x to the 4th plus x, right? So taking the derivative of this thing, now we can just take the derivative of these individual parts, right? So what's the derivative of 1/2 ln of x minus 2? Follow the derivative, the log derivative rule. That'll be 1 over, sorry, not 1. It'll be 1/2 times 1 over x minus 2. And the derivative of x minus 2 is just 1. So we leave it like that. All right. Now taking the derivative of this term, that's minus 1/2 times 1 over x to the 4th plus x times the derivative of x to the 4th plus x. Let's see. That'll be 4x cubed plus 1, right? So now you can go ahead and simplify the right side. What do you get? You get 1 over 2x minus 4 minus 1 over 2 times x to the 4th plus x. Yeah, I might as well just keep this like that. I'm going to undo that. And actually, this is 4x cubed plus 1 on the top, right? So that's the derivative of the right side. And now what we have here is we still have 1 over fx times f prime of x, right? So that's what the left side is equal to the right side. We want to find what f prime of x is, so we can just multiply now fx on the left and fx on the right. Because what does that do on the left? Well, that cancels out these two things. So all we're left with is f prime of x, which is what we wanted to solve for in the beginning. So f prime of x is equal to 1 over 2 times x minus 2 minus 4x cubed plus 1 over 2 times x to the fourth plus x. This whole thing times f of x. What is f of x? Well, it's our original function. So it's times the square roots of x minus 2 over x to the fourth plus x. And that is our final answer, right? So the overall process you want to do with logarithmic differentiation, first take the natural log of the function you're given with. It should simplify to something nice. Otherwise, what's the point of using logarithmic differentiation? So in this case, when we took the natural log of f of x, it gave us this lovely two-term equation where there's no fractions anymore. And then when you want to take the derivative of the natural log of f of x, because then you get this form right here, 1 over f of x, all of that times f prime of x, and that's will be equal to the derivative of the nice simplification you did earlier. From there, you simplify and you can solve for f prime of x. Usually what will happen is you'll be multiplying the right-hand side of the equation by f of x, your original function. So I believe it's safe to say if you're doing logarithmic differentiation, you should, in your final answer, multiply the original function somewhere within your final answer. All right. So that is a good example for part 4. Looking at part B, I might skip some of these for now. Let's go ahead and do C. We have 20 minutes left. We're halfway through. I'm going to skip B and C for now, just so I can get other problems in here. Looking at number 5, we've got, okay, we're doing word problems now, related rates. So each side of a cube is increasing at a rate of 3 meters per second. What rate is the volume of the cube increasing when the volume of the cube is 125 cubic centimeters, right? So how can we write this in terms of variables we understand? Well, if we let the side of a cube be s, then the rate at which the side is increasing, right, is going to be ds over dt, or simply s prime, is equal to 3, right? 3 meters per second. So ds over dt, s is the side, so that's meters, t is in time, so that's seconds. Or I'm going to write it as s prime just to keep it simpler to write, cleaner to write rather. So now the question is, how do we find the volume? So we're trying to find the volume's rate of increase, volume's rate of change, right? So we're trying to basically find dv over dt, which I'm going to write as v prime. How do we find that? Well, we're going to need to use our equations that we do know. Well, what is the volume of a cube? The volume of a cube is just that, right? Its volume is equal to s cubed. So how do we find the rate of change? Well, if we take the derivative in terms of time of both sides, what do we get? Well, we get this thing right here. We get v prime is equal to, actually, no, it might be better to write, yeah, I'll go ahead and write dv over dt so that we can see that it's a rate. dv over dt is equal to the derivative of s cubed in terms of time. Well, that's just power rule. It'll be 3s squared times the derivative of s, so that'll be ds over dt, right? And well, what do we know? What do we know here? Let me double check. Yeah, so we're trying to solve for the change in volume. So, and we're going to need the side and also the change in the rate of change for the side, right? So we know that this part right here, that is equal to 3, because that's the given. What is s squared? Well, we're going to need to derive s. Look at the last piece of information they gave us. They gave us that the volume, our initial volume, is 125 centimeters cubed. So can we not use this formula to derive what s is? Because we know that the volume is 125. So s is just going to be the cubed root of 125, which just so happens to be 5, right? So that means S is equal to 5. So this is go ahead, making sure that you not only know what equation is based off of the given object, but also being able to use the equation based off the given information to find the missing information, right? So we're trying to find dv over dt. We needed s and the ds over dt. They gave us ds over dt. We need to find s. We found that s was 5. So let's plug everything in. 3 times 5 squared times 3 is equal to 9 times 25, which is equal to 225. Right? So this is the rate of change. And if you need it, if your professor cares about units, it's very important you understand what the units are. What is the unit for volume? It is, oh, there's something I did wrong. Something that you need to watch out for is the units. 125 centimeters cubed. Okay, let's put everything in centimeters cubed because that might be easier. Would it be easier? No, it wouldn't be easier. Yikes. Okay, so the issue that we ran into is the volume they gave us is in centimeters cubed. We're going to need to convert that first into, actually, no. So this is 5 centimeters. We need to convert that into meters. So this will be 0.05 meters. So rather than that 5 squared, it's 0.05 squared. So it'll be 9 times, what is 0.05 squared? Let's just go ahead and calculate that for us. Why don't we? 0.05 times 0.05. That is times 0.0025, I believe is what it said. Yep, and then times 9 is 0.0225, and this will now be in meters cubed per second, right? So the reason why I did all that conversion is because the units, we need to make sure that they're the same. I went ahead and changed the side length into, because the volume was given to us in centimeters cubed. So we found that the side length would be 5 centimeters or 0.05 meters. I kept everything in meters because the rate of change for the side is in meters. You could have changed this into centimeters instead. Either way, you'll get some decimal answer or some really large number. So it's your preference. But yeah, make sure you match the units. Otherwise, you might get a wrong answer. All right, let's look at number 6 now. What do you got? A water tank shaped has the shape of an inverted square pyramid. Okay, so that just means it's an upside down square pyramid, right? With a length of 2, so, and then a height of 4. If water is being drained from the tip at 3 meters per second. Okay, so that means the volume is decreasing at a rate of 3 meters cubed per second, right? So decreasing, we indicate it with the negative sign, right? Find the rate at which the depth of water is decreasing when the water is 1 meter deep. So our initial height, okay, let me think about this for a second. So if we sort of look at it from the side view, the overall height is 4, but what they're saying is we're trying to find the change in height as we measure from the top. So this will be h, and it's decreasing, right? Find the rate at which the depth of water is decreasing on the water. Oh, it's decreasing. So rather than, got it, never mind. So they're measuring height from the bottom. Yeah, so this, let's say some arbitrary h value right here. So, and we're trying to find the change in that height because as the water drains, right, this height will continuously go down. That's how we match the question saying that the depth of water is decreasing. Okay, so let's go ahead and figure this out. So we're probably gonna need the, so yeah, the depth can be sort of considered as a height in a sense, measured from the bottom up. And what we're going to do is we're trying to find the rate of change of the depth. So we're trying to find dH dt. So in order to do that, the only equation we can form is the volume of this pyramid. In case you didn't know, the volume of any pyramid with any regular base is simply 1/3 the area of the base times the height. In this case, the area of a base is a square. So it'll be 1/3 of the length squared times height, right? So that's our volume. And in this case, what do we want? We want to find the change in height. So we're going to take the derivative in both sides. That will be 1/3. This is power rule, power rule and product rule. So product rule, take the derivative of this first part. That'll be times 2L dL over dt times h plus the derivative of the second side. So it'll be dH over dt times 1/3 L squared. Well, what information do we know? We know that dV dt is 3 meters or minus 3 meters cubed per second. Fortunately, everything's in meters, so we don't have to do any unit conversions. So you 2/3 L is 2. We do not know what dL over dt is. We do know that the initial height in this case is 1, right? Yeah. Yeah, the initial is 1 plus dH over dt is what we're trying to solve. Then 1/3. Oh, I see the mistake I'm doing here. There's an issue with what I'm doing. We're gonna need to go back a bit. So as we can see from this equation, at least, let me go ahead and rewrite the equation so it's a little cleaner to look at. dV over dt is equal to 1/3. Both of them have 1/3, so I'm going to factor that out, times 2LH dL over dt plus d8, sorry, no, L squared times dH over dt. And so basically, in order to find the change in volume, you'd need the length and height at the point you're looking at, as well as the change in length as well and the change in height. So we're going to need to first calculate some things, because in this case, we're trying to solve for dH over dt, right? However, we know what this is. We know what the change in volume is. Do we know what the height is? The height is going to be 1, right, of the pyramid right here. So we're going to need we don't know what L is though at this height, and we also don't know what the change in L is at that height. So we're going to need to calculate those first, I believe. So in order to find the length at that point, how do we do this? Well, actually, the length is proportionate to this height, I believe. Since we know that is that true though? Let me double think this real quick. In order to find the length at that point, we'd also need to know what the volume is at that point. Yikes, this problem actually is a little bit harder than you think, right? And the depth of water is 1 meter deep. I'm missing some information here. I'm missing I can't think of what I'm missing. length of 2, height of 4. Is there a way to relate the length of it to the height? Yeah, there is a way to relate it, actually. So here is the relation. If we have this let me write it on the right here. Let me draw it in a different color. Yeah, I think this is going to give us the answer. So if we look at the side view of the pyramid, that's a horrible drawing. The side view of the pyramid, we know it's two right triangles. This max height is 4, and this max length is 2. If we take a look at just half of this, we know this is 1, this whole thing is 4, right? And we're trying to find when the height is 1, so a triangle right here. So when this part is 1, these are both right triangles, and we're trying to find what this x value is. Well, if you know similar triangles, you can make the ratio. So if I say x over 1 is equal to 1 over 4, what does that mean? That means that x is equal to 1/4, right? So that means that the length, well, that's just half of the length. So if we go ahead and look at the whole triangle now, that means L at that H is going to be 2 of x. So in this case, L is 1/2, right? So there we go. That's our information. So this right here, we now know. We know what L is. Do we know the change in L, though? Do we know the change in L? That's a good question. Can we derive the change in L? Might be missing something pretty obvious, but I just can't see it, huh? Where do you find the change in L? Would they both be decreasing at the same rate? Is that a safe assumption? Let's see, is it a safe assumption? As x decreases, h also decreases, but by what rate? Yeah, no, these I see what's going on. I could be wrong, but I'm pretty sure the length and height are actually going to, the change in these are going to be the same factor. No, that's not it. That's not right. It will be damn. It won't be the same factor. So in order to find the change in length, what should you do? You should consider yeah, I'm missing something here. So we've got about 5 minutes left. We're so close. I'm just missing what this part is right here. If those of you watching, if you know what I'm missing and you know how to solve it from here, congratulations. Hopefully I'm correct in finding the length like this. And yeah, I'm really upset. How come I cannot figure out what the change in height would be? Huh. See, the height decreased by a factor of 4. So divided by 4. 2 divided by 4 is 1/2. Yeah, no, it's not ringing a bell. So I apologize for that. I cannot remember how to take it from here. But I'm going to assume that you guys have notes on type problems like this. So you should be able to figure out what I'm missing. And from there, it's just algebraic simplification, right? You'd solve for dH, which if we go ahead and just rearrange the problem, it should be 3 times dv over dt minus 2LH dl over dt all of this is times 1 over L squared, and this will give you dHt. Yeah, and it should be a negative number. This will be some negative value. And I think because the question's saying that it is decreasing, so since the question already assumes it's going to be negative, you don't need to write the negative as your answer. Well, if you're going to write out it's decreasing at, then you just write the number there. You would not write the sign because the decreasing represents the negative. If you're just going to write the equation in this answer, then you have to write the negative as well. But if you write it in word form, decreasing at just the magnitude of the number, all right? So yeah, that is 6 for you. I'm missing something. I apologize for that. But yeah, there's only 2 minutes left, so I'm going to wrap it up. I'm just going to probably give you some pointers, at least on the setups for some of these problems. 7 has 2 cars at the same point. When the cars start driving, car A travels east, car B south. How fast is the distance between them chasing? Okay, well, here's the question. They start at the same point. Let's say that this is the origin if you want to make it simpler. A is going east, which is right. So A is traveling at a velocity of, what's that, 40 meters per hour. And then B travels, that should be smaller, technically. B travels at 30 meters per hour. This is B, and this is VB, VA. You're trying to find what the rate of change in the distance between them is, right? So set up an equation, right? After 1 hour. So what is their position after 1 hour? So at t equals 1, you have this sort of triangle, 40, 30. If you did the math, it should be 50. So this is at t equals 1. So you're trying to find d, instead of distance, let's go ahead, instead of a lowercase t, let's make this an uppercase t. So you want to find the distance between a and b. So the derivative of d in time will be something like that. And you see that the relationship here will be Pythagoras theorem, right? So it'll be, we know that this, let's say this is A, this is B, this is, say this is D, capital D. So A squared plus B squared is equal to D squared, right? So if you were to take the derivative of both sides, you get 2a dA over dt plus 2b dB over dt is equal to 2 capital D dt over dt. And this is the equation you sort of use. You can see you can cancel out all the 2's. And yeah, from here, you know what A is 40, B is the initial value, that's 30. D, we know is 50. So then you know the rest of the rates too, right? So that's the setup for there. And the rest all similar. You have to figure out what equation you're using. Spherical eraser, surface area. So you're going to need to know the surface area of a sphere, which I believe is, I don't remember it off the top of my head. Let's just look it up. Surface area of a sphere is 4 pi r squared. So if you want to find, if you find the derivative of the surface area, that'll be 8 pi r dr dt, right? And that's your sort of formula there. 9 is finding the differential again, so we'll skip that. And linearization, just remember the formula, Lx is equal to f of a plus f prime at a times x minus a, I believe is the formula. Let me double check. Yeah. So in this case, you just find each individual thing. F of a is very straightforward. Plug it into the original function. X minus a is very straightforward. And f prime is very straightforward as well. You just need to find the derivative of this. So 1/2 times x plus 1 to the -1/2, right? And then plug in a there. So this one I'll quickly solve. F of a is the square root of 1. No, yeah, square root of 1, which is 1. Yeah, 1 plus 1/2 times x minus 1. Sorry, x minus 0, so it's just x. Yeah, so it'll be that, I think. So to skip ahead of steps, so just confirm that on your own. But yeah, so I ran out of time, so there was quite a bit of derivatives in the beginning. So if you're pretty comfortable with derivatives, I'd focus on these word problems, because some of them, like that first one I did, was you might forget some things like I did. But anyways, yeah, so general tips for you guys. The things that we recall that we're going to need to remember, we're going to need to remember a lot of different equations for volumes, areas, triangles in general, just different formulas for different shapes. And then remembering all your different derivative rules and nested chain rules specifically, those get a little complicated, particularly when you're doing nested chain rule with trig functions. Those get really complicated. But yeah, that's all I have for you today. Make sure you guys get a good night's rest beforehand, eat a proper meal before your exam. And yeah, that's all I have for you guys today. Thank you for watching on home. And if you guys do have any questions before your exam time, feel free to come into the Math Center. We're open from 9 a.m. to 4 p.m. Monday through Friday, and we're open online as well as in person. So whatever works best with you. But yeah, that's all I have for you guys. Thanks for watching. Bye-bye.